Thank you, guys. Yeah, I flew all the way from Berlin to Bergen. Same weather, unfortunately. Yeah, I'm a CEO and co-founder of NetBird. I'm also a software engineer. And at NetBird, we are building a network security platform, actually open source network security platform. That's very important. And that allows engineering team to connect to remote private resources without opening ports, security groups, any other firewall trickery. And yeah, as I said, I'm a software engineer, but mostly I'm doing it now for meditative purposes. And if you go into this repository, you still can find my commits. But yeah, let's get started. Where's the clicker actually? Oh yeah, I don't need it. Yeah, all the private networks and in particular NetBird basically have main use cases, and access to internal resources without exposing them to the public is one of the biggest ones. And one of the features that we have at NetBird is DNS management and access to these resources by private names. So these are the core features. And to make it a little bit structured, I prepared this agenda. So first, I will touch on the need of DNS in private networking. Then I'll show you how to implement a DNS resolver in Go, just briefly. Then the DNS port issue on Linux. So that's actually the core of the topic, the issue that we faced. Then a quick look at eBPF and XDP. So these are the cool technologies that we used for the solution that I will show you in the last slides. So first off, NetBird is a high-performance peer-to-peer network based on WireGuard. And in any private network, especially in peer-to-peer networks, you have devices that are running client applications, and they establish direct tunnels between each other. We call it agent, but this word is currently reserved by AI folks, so let's call it like client app. In order to communicate, these machines need IP addresses. So these are the private names, and you can either assign it manually, or you can use some sort of a coordination server, like brains of the network, that will distribute these names, the IPs, and assign to the machines. So that's the case for NetBird, by the way. We have the coordination server that does this. It's like a core component in the architecture. So to make it even more convenient and user-friendly, we assign, or this coordination server can assign private names, so that you call your services, including Kubernetes services, by names, by private names. And then essentially our task in implementing this feature was to resolve this to this, right? Very simple thing. It can be a map or a dictionary in a programming language. But it's not that easy, actually. So, and probably you wouldn't be here if it was that just resolve this name into the IP via map. And as a reasonable and pretty much like any engineering team does, we started brainstorming and multiple solutions. So the first one is a centralized resolution, which is not really a suitable case in our case, but it was very obvious. Like, you run a server somewhere, and then it resolves the names by clients calling this server. Given our scale, and we have millions of devices, that would be actually a problem. Like, we will have to solve another problem of scalability of this machine, and it's also dependency, so that the clients have to always communicate with this external service. So that was a no-go. Then someone suggested to use a local hosts file, and then, yeah, I already see the faces like, that was no go, and in fact, this person doesn't work in our company anymore. I'm joking. We welcome any kind of ideas. It helps with brainstorming. But you know the problem here, like the file gonna grow, and it's just not really nice. And we didn't even really discuss much this solution. So the one that really worked for us, or we thought worked for us, was a local resolution. So the idea was to create a local service, DNS service, that would resolve the names on the machine, and we would pack it with our client application. So, well, let's do it. You know, that's our engineering team. Very brave, and again, as a pragmatic team, we started looking for ready implementations, and it's a helpful thing actually to implement the DNS service. But thanks to this library, we didn't have to do a lot. We still had to do quite a few things, but this library is a collection of DNS-related fundamentals, you know, like you can build your server using this library or client, and it's written in Go. So check it out. Thanks to Mick for this library. So we use it in NetBird. And the interface looks pretty simple. It's like an HTTP server, right? You have a listen, stop, register handler, and this is the part where you register the resolver for your names, right? So very, very straightforward. And then we started implementing it. No, we didn't do that. So because it's actually pretty risky in network security to do these kind of things because of these hallucinations. And back then, when we were implementing the solution, they were not good. They are still not good, right? But you can try. Like if you can do it by the end of the session, implement your resolver, maybe we get you some swag or T-shirt. But yeah, maybe a little bit off topic, but we use AI in our team, but we use mostly for like integrations that are not core connectivity. So for example, we have integrations with EDR or IDPs, and there is already a template for Claude, for example, to just pick the existing integrations and do the same thing. So these kind of things are okay, but networking is really tough. I really don't know who can vibe code networking stuff with AI. So yeah, so we used a very old school approach. We just coded it ourselves. So we have our resolver, and it listens on the port 53, which is the default port, DNS port. And the second thing we had to do in our application, in our agent, is to configure operating system to resolve this private namespace, our network namespace, to point the resolution of the private network namespace to our resolver, to our embedded resolver. Once again, great. So we have a resolver. We just call the operating system. We configure it. Done. No. So that wasn't really the case. And you know what this is? Actually, the picture goes all the way down. So it's a timeline of Linux distributions. And we, as a network security company, we're trying to make it so simple so that nobody has to configure anything, and we don't want people to bother with configurations. And we need to support lots of this, right? And I'm not saying that it's like a very common case, but sometimes people have old systems, and when they run NetBird there, they encounter issues, and we just want to solve all these issues. So, but specifically the problem is that on some operating systems, Linux operating systems, you cannot change the port 53 to anything else. So you cannot run a process that is doing resolution and then configure operating system to resolve this namespace on some port different than 53. You can put whatever, but it will be 53. So it just wouldn't work. To be honest, I don't remember what were the systems, but I think even Ubuntu, like below 16 or something, like they had this kind of problem. So you cannot change the port, and that means that if there is already a process running, you cannot spin up your resolver on this port because it's occupied. Yeah, we started solving this problem, and that's one issue that we faced, and this is one solution for that issue. And we call it unassigned loopback address trick. And what it does, it basically you can run multiple processes, but assigned to different IP addresses. Like, for example, you have a process that can bind to 127.0.0.1, port 53, and then you have another process, and that would be our resolver, if the first one is already running, that binds to 127.0.0.153, and the same port 53. And this would work. And the reason why we chose the unassigned loopback range is because you don't need an actual interface, network interface on the system. You just put this into configuration and you can listen on the port. Because if you have like 192, 168 or so, you actually need the interface created on the system. Well, this is the code that demonstrates that we used to test the idea. So you see that first lines, the first line 127.0.0.153, and the second listener, and here I'm just starting 2 listeners, and when I run it, it works. So we have 2 listeners that are listening on port 53, different IP addresses, perfect, right? And well, it wasn't the final solution. So, and thanks for, if there are some network administrators, guys, I love you, but you know, sometimes you do some interesting things. And like we released the version, you know, we send it to test users, and some of them came back and said, well, if I'm listening on all interfaces, it won't work. So DNS won't work. And once again, the DNS is actually it's a core. You know, if you're calling a service by name, you cannot resolve it, you cannot access it. So you can't access Kubernetes clusters, you can't access databases, so it just won't work. And what's the solution to that? Yeah, once again, a pragmatic team, we decided to close the shop and stop doing this. Because at some point, you know, it was frustrating, but of course we didn't do that. We looked for alternative solutions. And, oh yeah, that's actually the demonstration. Sorry, I went a little bit too far. So that's the same code that I showed you before, but I have this first listener listening on all interfaces. And the first one starts, right, 000053, but the second one fails because obviously it's not allowed by operating system. So we started looking for a solution, and we found XDP, because we already knew eBPF. We use it for some other purposes, and if you are not familiar with these technologies, these are really great tools. And eBPF is something that allows you to run custom programs that you write yourself within the kernel of the operating system in a safe way. So it's like a sandbox environment where you can execute some operations. And it's very fast. So it runs within the kernel of the operating system, and there is no switch from the kernel to user space that makes it slow. And for that reason, WireGuard, by the way, the kernel WireGuard on Linux is very performant because it runs in the kernel of the operating system. And XDP is something that allows you to quickly get access to the packets once they left the network interface. So you can attach an eBPF program to a network interface with XDP, and it will give you an access to the packets. So you can actually override packets, you can read them, you can do some telemetry. So actually some observability companies use that as well. So you can do magic with these tools, really, but you have to be careful. These are very powerful. And yeah, so this is the final solution. I tried to compress it a little bit, so you have to be paying attention to to the whole flow. But what we've got so far was a local resolver, and that's an application which is embedded in our agent, in our client networking application, and it listens on port 5053 or whatever other port, like can be a random port. It's not port 53, that's important. So it's some random port. And the second thing, we configure OS with a fake resolver to resolve our private namespace, basically by this resolver. And this resolver doesn't have anything behind it. So it's just a configuration. There is no process running with this port. And it's important, it's port 53, because remember, we cannot change it on certain operating systems. So we configure the operating system with this resolver. And by the way, this name, this IP is a private IP of the network. It actually can be some other name, but we used our network IP. So we configured the operating system with port 53, fake resolver, nothing behind it. And then we created this program, eBPF program, that would essentially catch the DNS packets, go into port 53, and then override them to port 5053, which will be the routing, basically. So we route the packets from port 53 to port 5053 to our actual resolver. Yeah, to better understand this, here's the flow. The DNS client, so whenever you're calling a service, right, it can be a Kubernetes service, can be database, you call it by name or something in the browser, HTTP service. Your browser client asks the system, give me the resolver for this namespace, for this domain. So the operating system sees that the configured resolver is the fake one with port 53. It gives it back to the client, and the client sends a request to this fake resolver, but there is nothing behind. And our job is actually to catch this packet by port, right, by destination, override it to port 5053, and pretty much just route traffic to the actual resolver that is running within our application. So our local resolver receives this packet, resolves the name, and it sends back the response. The problem is that the packet that is sent back to the client that requested this query has the source of 5053, and the client doesn't know anything about this port because it didn't send a request there, right? And if it would receive it, it would just discard the packet. And we use the same program, basically, but other way around. We just swap the ports back. So from 5053 to 53, and we send it back to the client. The client is happy, the name is resolved, and that's pretty much the whole flow of the solution that we implemented. The program itself, BPF program, was written in C. It's pretty simple, and hearing these words like XDP, BPF, hijacking, it's very scary. But in fact, that's the core of this idea, right? You have here a section that catches the packets on port 53, catches this fake resolver address, puts it to 5053, and passes the packets further. And at the bottom here, it's doing it the other way around. It catches the packets with source 5053, source port, and overrides it to port 53. So pretty simple program. And the first line is read settings. This is something very helpful too. So this you can use in your BPF programs to exchange data between BPF program and a user space program. And in our case, we just use it for configuration. So there was nothing really magical here. We just passed the IPs and ports to the program, but you can exchange data, like, you can fill the data. It's called BPF map, and that's like a data structure that connects your BPF code with user space code. Another library that we used, and thanks to the Cilium contributors, is called BPF2Go, and name is very clear. It states that it converts BPF to Go, so you can use actually your BPF program in Go. It creates helper classes or structures. I'm using my Java jargon from the past. And it's very handy, so check it out if you are interested. And maybe the final words. This is what an experienced product manager gonna say. This is a tiny feature. You can do it in a few hours. And indeed, it looks very, very, very simple, but in fact, it wasn't. It took us like a few weeks to come up with the final solution. You find one problem, then another one. And usually, if there is something that looks very simple, there is something complex behind, right? And all the code is open source. You can check this repository. There is a DNS package. You can see how we used it. There are some other things with eBPF. Give it a star if you want. And we have a Kubernetes operator, which makes it very easy to expose private clusters to your internal network so that you don't need to make them public and always hide your infrastructure from the outside world. Yeah, that's it from my side. You have a question already?
So you create kind of service mesh at the kernel level without the whole service mesh complexity, like just on service resolution.
Yeah, so it's a pretty much a remote access solution. So you can access. We create a virtual internet for your resources. So you can have Kubernetes clusters, you can have databases, even manage services without exposing them to the public.
But you create also like a network between them, so like find each other.
Yes, so it's pretty much a virtual private network, but it has this peer-to-peer flavor in it. So there is no central server. Only the coordination one that configures the system, but the rest is peer-to-peer. So I guess you opened the question and answer session.
Any more questions? Yeah, from David in the back.
Thank you for your talk. I think it's really cool to go down the eBPF and XDP route, but could this have been an IP table rule?
It actually could be, yeah. But it's nicer to use these tools because it's actually like more programmatic, and it's also harder for network admins to actually break it, because then the IP tables, someone sees these rules, they can be changed, but yes, it's possible.
And do you chain the DNS back to the host resolver, or do you take resolution of everything?
No, it's not everything, only for this specific namespace. And to add, we also detect what resolver is used on the operating system, and we actually have like if-then statement in the code. We check if it's managed via a host file or a systemd resolved, and we try to use it. So we try to detect and use the processes that are already running on the system. And I have to say that this solution was an edge case, but we want to really make sure that the experience is great, and yeah, people try to run things and then it doesn't work, they are frustrated, and we want to, I think there was too much of frustration in networking, and especially in the virtual private networking world. So we are trying to solve it.
Especially DNS.
DNS, yeah, is a pain.
There's also frustration with DNS.
Yeah. And we are still improving the system. It's not that we have all-in-one solution, but it's evolving. The product is evolving.